Aloha and welcome to our video on the sex chromosomes. And the goals for this video are to describe how an organism's sex is determined. We'll explain a little bit how sex-linked traits are inherited, and finally we'll take a look at a pedigree. Okay, if we return to a picture of our karyotype here, what we notice is that we have 22, this is a human one, we have 22 what we call autosomal chromosomes, and that's going to be all of these up here, the ones with the little number under them. These are going to be the ones that we get, one from the mother, one from the father. They both look about the same, they both have the same genes on top of them. So we have our full set. We look at it that way. What I want you to notice is there's one down here that's going to be a little bit different. And the one that's a little bit different, and we'll see it, it's right down here. And these are what we call our sex chromosomes. And in this individual, we happen to have a male. We know that because we have one X and one Y chromosome. Okay? So if we go over to our Punnett square over here, we'll notice that our female parent, she's going to be homozygous for the sex chromosomes, which means all that she has, her genetic makeup, is going to be XX. So that all that she can produce are going to be these X gametes, and that's all that she contributes to the scenario. The male parent, on the other hand, is a heterozygous individual, and he has the XY condition. So he can give an X chromosome or a Y chromosome. So it's truly the male's gametes, the sperm cells, that are going to carry that Y, which will determine whether you have a male or a female child. Okay, one of the interesting things about the sex chromosomes is we have this inheritance of sex-linked traits. And what we're talking about primarily is we look at the X chromosome and we'll see that it has some things like hemophilia is the big example they use, color blindness is another one. You can have Duchenne's muscular dystrophy. You have all these different things that are going on the X chromosome. Now, the Y chromosome, because it's a different shape, it's a different chromosome, it doesn't have those same genes. So if we jump over to our example here and we talk about hemophilia, and remember, hemophilia is a disease where this blood does not clot. So if you were to get a cut or something like that, you don't form a scab, you would bleed out per se. So it's a real dangerous threat, but we can take care of it a little better in modern times with medicine. But back in the Middle Ages and things, it was a lot more lethal, to say. Now, what we'll notice is when we look at the mother here, our mother is what we call a carrier. And that means that she has the allele for hemophilia, but she also has this dominant trait that does not have that allele. And because she has this dominant trait, she doesn't show any signs of hemophilia, but she's called a carrier because she carries that genes with her. Now, the father is normal, so you're going to notice that his X chromosome is going to be that dominant normal type as well. Now, when we fill in our Punnett squares with X's and Y's, we fill in a Y for that blank part. Okay, so this one here, you'll see this Y come down. This is what determines we have our sons. Now, because the mother has a normal chromosome, we have a daughter here who's going to be homozygous normal. Okay, we'll have a son here who is normal, but the mother also carries this hemophilia gene or this hemophilia allele. So we'll have a daughter here who's also going to be a carrier. Now remember, she's a carrier because she has a normal gene and that's what she expresses, but she's also carrying this hemophilia gene as well. And then unfortunately they have a son here who is going to be a hemophiliac. And you'll notice he has this allele here from the mom of the hemophilia, but because the dad gave a Y, that's the only one that's going to be expressed. So we a lot of times see these sex-linked traits show up a lot more in males than females because they get one chance and they're done. They don't have the ability to have it masked with another normal chromosome here. Okay, so let's take a look at a pedigree. And a pedigree is kind of like a family tree, but it'll allow us to track a trait or a specific allele for a trait through generations. So we use these a lot of times to trace illnesses or to trace genetic conditions, and it explains why it'll skip generations or why some individuals have it and some don't. When you're reading these, you want to remember that a circle is a female and a square is going to be a male. And then when we have this horizontal line in between here, that tells me that those two individuals are going to be married. Now, a product of the marriage is going to be the kids. So these are going to be their 3 kids. And we notice that they have one male that possesses the trait, a female that does not, and then a female that does possess the trait. Now, these children, some of them are going to get married, And as they get married, we'll notice that we have here a female that is infected and a male that has the trait. And that'll bring us down, and we notice that we have two individuals here, one infected, one not. Okay, so it allows us to go through and we can kind of see where that trait is and how that trait's being passed on from generation to generation. Now, as always, the lessons will go into a little more detail. Good luck with your lessons, and we'll see you in the next video.